Please.
Thank you very much, Alessandro, for the introduction. I'm very happy to be here. As I understand, most of you are not familiar with lattice QCD. Is this correct? I think only one, maybe? You know, so you will excuse me or correct me if I... there are two lattice people? Very good. Okay, so what I would like to do today, I understand that I have 4 lectures of 1 hour. So I will spend today sort of introducing to you lattice QCD. Of course, it's very hard to do it in 2 hours to go into a lot of details. So that's why I prepare slides. Hopefully I'll go a little faster than on the board, but please stop me and ask questions. If we don't get through all the material, you can have access to the slides and the literature, so you can continue on your own. And tomorrow, my plan is, after we introduce lattice QCD today, here is Simone Pacchio, then tomorrow I will spend 2 hours really telling you how I actually use lattice QCD for spectroscopy and structure. So tomorrow it will be more what we actually do with all this formalism, okay? Is it clear to you? Okay, so let's get started. Okay, so this is the introduction for today. So it's more motivation. This you all know. You have heard the lecture, so I go very fast. Then I will introduce how we discretize quantum field theories. And then, of course, I will go to gauge theories and say a little bit how we take the continuum limit. And then in the next hour, probably I will not cover all these in details, but in the next hour, we continue with how to put fermions on the lattice. Okay, so the standard model, you all know, I'm going to be very fast. We discover all the constituents. So we know a lot about the standard model. You have heard a lot. You know how to do perturbation theory for the electroweak sector. So there you are all set, and I'm not going to say anything. However, the standard model also has a theory of the strong interactions that was written down actually 50 years ago. We celebrated last year, the 50-year anniversary. These are the people who wrote down originally the Lagrangian. In 1974 was published. And the tag, so this is a beautiful equation. It's one-line equation. And this equation contains all the strong interacting phenomena, hi Angela, in the universe. So it looks very simple. It's written in terms of the gluons, here they are, and the 6 quarks, that's the sum over F. And the task is to really solve it. So it's nice to write an equation, but unless we solve it and get the number out and give it to experiment, we cannot check whether this is a viable theory. So you all know the basic properties of QCD, asymptotic freedom. The coupling constant decreases at high energies, so we can do perturbation theory at high energies. But at nuclear scales of 1 GeV, this is no longer a perturbative theory. And this is where I am interested, how to solve and get results in the nuclear regime, at nuclear scales. And the other fundamental property is confinement, right? Quarks and gluons are permanently confined. This is, again, a unique property of QCD. And here I'm showing you some early calculations in lattice QCD, where indeed you observe confinement because you have a linearizing potential. A linearizing potential means that if I take the force, this is a constant force, and therefore if I want to extract a quark and anti-quark, I will need infinite energy. And therefore, by definition, lattice, QCD, not lattice QCD, QCD predicts confinement. These three people got the Nobel Prize for discovering asymptotic freedom, Gross, Wilczek, and Polzer. So these are two fundamental theories that we use in lattice QCD. It's well defined to do what we do because of asymptotic freedom, basically. The theory is asymptotically free, and therefore it has a well-defined continuum limit. Right, so let's see a very simple system where we understand the basic difference between electromagnetism and the strong interaction. So suppose I look at the simplest atom, the hydrogen atom, and I want to calculate the mass of the hydrogen atom. Okay, well, we know the mass of the electron is 5.5 MeV. The mass of the proton is 938 MeV. And if I compute now the binding energy of the hydrogen atom, I find 13.3 electron volts. Very, very small compared to the masses, even compared to the electron mass. And this is why I can do perturbation theory, because it's a small correction to the sum of the masses. And this is what holds the hydrogen together, this little binding energy, right? Now, if I look at the proton, this is a very different system. We know that the U quark mass is 3 MeV, then down quark mass is about 6 MeV in some scale. So if I add them up, I get 12 MeV. However, the mass of the proton is 939. It's a very, very big correction, which means this system is very different from a hydrogen atom. And most of the mass comes from the strong interaction. So this gives you an idea why we may need a different method to compute the binding energy of the proton as compared to the binding energy of the hydrogen, right? So everything is interaction. So the vast majority of the mass in the universe actually does not come from the Higgs mechanism. It comes from the strong interaction. And therefore, it's intriguing to understand the mechanism of mass creation in the strong theory. Okay, so why we put QCD on the lattice? I sort of motivated this by telling you how different it is from electromagnetism, where we do perturbative calculations. We have written the equation of QCD. However, as you know, in quantum field theory, it's not enough to write the Lagrangian only. You have to tell me how to regularize the theory and how to renormalize it to get rid of infinities. And for the electroweak theory, Truth showed us how to do this in perturbation theory. But in strong interactions, we cannot do perturbation theory at the nuclear scale. So how do we define the theory rigorously? So the only framework that we know today how to define, how to regularize this theory is to put it on the lattice. And this was done by Ken Wilson in the famous 1974 paper. So we discretize space and time. So the lattice acts as a non-perturbative regularization scheme. And this is because it provides an ultraviolet cutoff. The biggest momentum you can have on the lattice is pi over A. So this is an ultraviolet cutoff. And therefore, you regularize the ultraviolet infinities. So one proves that renormalized physical quantities have a finite, well-behaved limit as A equals to 0. We will see this later on. Okay, so this is how we regularize non-perturbatively the theory. But furthermore, it's useful because we have a formulation where we can simulate the theory using methods which are equivalent to statistical mechanics. So doing simulations to compute observables. So this provides a definition of the theory, and as we will see, it also allows us to do computations to actually compute various quantities. The important thing about lattice QCD is not a model. So some people call it a model. It's not a model. It is a rigorous definition of QCD, okay? It has exactly the same input parameters as a continuum theory, namely the 6 quark masses and the coupling constant. After I give these parameters, these 7 parameters, there is no more freedom. Everything is defined, provided I take the continuum limit, okay? So there is no freedom to fix anything. After I put, like in the continuum theory, if I put the parameters in, I predict everything. So that's why it is a theory that we say is improvable as we go to higher sophistication in lattice QCD. Okay, so let us now do a little bit of more mathematics. So I will start with the scalar field. So I have the continuum theory, and I want to define it on a lattice. How do I do it? Okay, Simone will tell you how to do it in symbol Lagrangians. Probably some of you have seen it using the Feynman path integrals. Have you all seen this? Yes? Okay, so what I will do here is something analogous. So we know from quantum mechanics, we have X and P, and they have commutation relations. Now, for the scalar field, I will have phi and the momentum, the conjugate momentum. And I have states, which are eigenstates of the position operator. And similarly, I will have states, which are eigenstates of the phi operator. And here, there is a phi missing. And then I will define these fields on sides. Okay, I will define these fields on sides. So the continuum, Hamiltonian looks like this. And when I put this on sides, instead of continuous R, I have integer quantities. If I am in 3 dimensions, 1, 2, and 3. And I will have a sum over all the lattice points and the integral over the volume. So this is pretty straightforward. I define at each lattice point a scalar field. I discretize the derivative. So that's a discretization of the derivative. And I define my theory on the lattice. Okay, so this mu I denotes a displacement by one lattice side in the ith direction. Yes? Okay. Yeah, I take the continuum theory that I assume everybody knows, and I put it on the lattice. Yeah. Okay. If you know this, then I don't have to go through that. But okay. And then, like we do in quantum mechanics, when we want to evolve a state, a particle that acts to another position at a later time, We can do a time evolution here in path integral formulation, where I integrate now over all the possible arrangements of these scalar fields, right? And okay, here I have the time, and so this is the action of my field theory in the discretized form. And for these lectures, we will see in a minute that there are formulations that take the spacing in the time direction to be different from the spacing in the spatial direction. Here, I will take it equal. Okay? So I will take an isotropic lattice. Right, so this is what we said. We replace a continuum derivative by a discrete derivative. And then if I want to compute an observable, I will take the expectation value in the Feynman path integral formulation, where this action is the action of the system. Okay, now I already have done something here because there is no I in front of the action. So I already have done something here that is not what you do normally, and we will come back to this. Basically, I have rotated to imaginary time. And the reason you can do all the regularization in real time. This is not an issue. But if I want to do a simulation, then this is a step that has to be done. Right, so now, in order to make this a little more concrete, like as we said, we have eigenstates of the operator X with its completeness relation. I would like to define creation annihilation operators that are called coherent states. And because I'm doing bosons, these are bosonic coherent states. So what I want to define is a creation operator that acts on a state, and this you all know, right? Erases by one, and it annihilates. So I want to define now coherent states Z, like e to the Z of this creation operator. And this will give me this, I mean, if you put this and expand, you will get this expression. Okay, why do I do this? Because then I can manipulate and act with an A or Z, and I get Z the eigenstate. So this defines this bosonic coherent state Z, so that this operator acting on Z gives me Z, eigenvalue Z. And there is a completeness relation between these. So if I do Z, the overlap will give me this exponential. You can go and convince yourself that if you do this algebra, you will get this exponential here. And the completeness relation now is the equivalent of that, but having this exponential factor because it comes from the overlap. So that's how these coherent states are defined. And now I can present this instead of writing this product here. I can devise a notation that I call this, all these factors here d mu z. But this factor is really this product here over all the states. Okay, so now having done that, I am in the same position to compute the matrix element of the evolution operator in Euclidean space. Like we do with X, from Xi to the final one with the evolution operator, I do exactly the equivalent thing here. So I put complete set of states. I divide this in n time steps of delta t each. And I put in complete set of states that I have defined. And I do the algebra, okay? And I get the action of the system and this transition amplitude. Okay, so the transition amplitude is an integral over all these states, e to the minus the action of my system. So this resembles what we do in Feynman path integrals in quantum mechanics with these coherent states. Right, so now that we did the bosonic coherent states, I want to define the fermionic coherent states. So what I want to do again is to act with this operator that annihilates my state C, so that I have an eigenstate on the right-hand side with an eigenvalue XA. Now, if I multiply this equation with another operator, C, okay, here I have CB times CA, I will get this equation here. But because I know that fermions anti-commute, I have to have that if I interchange now these eigenvalues here or these numbers here, which are not numbers, I will get a minus sign. Because I know if I anti-commute these two, I will have to get a minus sign. So to be consistent, I have to have C anti-commuting with another C. Okay, so this defines a Krasmanian algebra. So instead of having commuting numbers, I have anti-commuting numbers, right? And therefore, C squared is by definition 0 because there is no other way to satisfy that. And for Krasmanian variables, I know that an integral over the C is equal to an integral over X star is equal to 0. And the integral over the C or star is equal to 1. It's like a differentiation rather than an integration, right? Okay, so now we can define fermion coherent states in exactly the same way as we did with bosonic states with this exponential here, which has similar properties to what we have seen before. And we can now construct path integrals using these Krasmanian variables. Now, remember, these are numbers. They are strange numbers. They anti-commute, but they are no longer operators. Okay, like in the path integral, I no longer have operators. I have numbers, right? Okay, so I have achieved the same thing now. And now let's see what happens if I integrate now over Krasmanian variables. So if I have a matrix of this form, and then a generating term here, J, this is also Krasmanian, Z star J, and I want to perform this complex integral. If these were bosons, I will get the inverse of the determinant. You agree? It's a Gaussian integral. It's a Gaussian, I can complete the square, and I get 1 over the determinant. So if these are bosonic variables, this is what I get. This you all know, you can do it as an exercise. Now let's do the equivalent thing, a very simple thing now, no metrics, just a number here. The complex integral over e to the minus a star ax. So I can expand this. The only term that will survive is the first one, because anything to any power will give me 0. And therefore, this is very simple to compute because the first term is 0, as we said. And the second term, because I have to anti-commute this and bring it here, it will give me -1. So this will become a plus. And then I will get A. So now I can generalize this for a matrix. You know how to do it. I diagonalize my matrix, and I can prove that now instead of getting the 1 over the determinant, I will get the determinant of whatever matrix I have here. Right? So this is a big difference between bosons and fermions. We get the determinant instead of the 1 over the determinant. Okay, so now if I have a general expression of this form, where I have integration over fermionic degrees of freedom and bosonic degrees of freedom, and my action is bilinear, which all quantum field theories to our luck are, because of renormalizability, then I can explicitly integrate out fermions. And I get the determinant over the bosonic fields. This is crucial for lattice QCD calculation, because there is no way I can represent anti-commuting numbers on a computer, of course. I can only have commuting numbers. So if I couldn't do this step, it would be a problem. But fortunately, all quantum field theories are bilinears in the fermionic fields, so I can integrate them out. At least QCD that I know, this is what we do. And therefore now, okay, what is the problem of doing that? This is a local theory. This has become a non-local theory because of the determinant. And this is a problem for, or it was for a very long time, a difficulty in lattice QCD simulations, because it's very easy to simulate a local action. It's much harder to simulate something which is not local, because the determinant, every time I change a field at one side, I have to recompute the determinant. And this is the problem. So it took many years to figure out how to deal with the determinant that appears here. Yes. This is a good student, you see, an example of it. Where there's a, yeah, you can do this transformation, Strakonovich transformation, but yeah, in principle, you cannot do this, what I'm saying here. But the crucial step is that here, what appears in quantum field, I mean, standard model, right? In the standard model, we always have bilinears. We have psi bar, an operator or something here, psi, right? So this is a Gaussian. And because it's a Gaussian, I can integrate it explicitly. And that's what allows me to get rid of the fermionic degrees of freedom. Okay. Okay, so now we are ready to compute fermion propagators. Okay, so how do I do that? Well, I want to compute the time order psi bar, right? So the functional integral representation, we have written it, right? It's whatever fermionic bosonic action we have, minus xi bar m xi, right? This originally is an operator. Now it has become a Grassmann variable. We integrate over all Grassmann paths, and the psi has become a xi, a Grassmann variable, right? So here I have operators. I don't have hats, sorry, but these are operators. And here now I have Grassmann, the equivalent Grassmann variables. Okay, so the only difference now is that I have this multiplied by the exponent that we have before. However, I can always differentiate with respect to xi bar. And bring one xi down, right? And differentiate with respect to xi and bring xi bar down, right? And if I do that, then what I will get is the inverse of this matrix. And here, I mean, this effective contains the determinant, okay? So it's not the original one because I will still get the determinant of M, okay? So I will get M inverse times the determinant of phi, and I have just put the determinant on S, and I called it S effective. Okay, this is proven here. So if you want to go through it, you can go through it here. You see, if I have any product of xi, sorry, this should be xi star. Okay, xi star, I have to have equal xi stars and x's, otherwise I will get 0. Then I differentiate this, this integral here, and I put n equals, after I differentiate, I put n equals n star equals 0. Okay, so this brings down the x's, like I said. And I would be left, I complete the square, and I would be left by this determinant to the -1. And then if I make the integrations, I get powers of this inverse m coming down. And the determinant is left, and I write it as c to the long determinant m, and I put it on the s. So it is proven here, all the steps. Here I said it a bit in a very past way, but here is proven really how this works out. So if I have n times n products of these bilinears, then I get n inverses of this determinant. And this determinant will be, of course, here, this matrix here would be the Dirac operator, and the inverse of the Dirac operator is going to be the propagator. That's why I get a product of propagators. Okay, and I have to pair all the indices, and so these would be the corresponding weak contractions that we belong in perturbation theory. So I get all the combination of propagators in this sum. So this is basically the weak theory. It is the weak theory, okay, that you know from perturbation theory. Okay, so this is extremely important because any operator here, which is written as bilinears of psi bar, can be written as a functional integral of a bosonic degrees of freedom again. So we get rid of the fermions. Okay, I haven't talked about boundary conditions, but boundary conditions, what we do usually for bosons, we take periodic boundary conditions, and for fermions, we take anti-periodic boundary conditions in time, and this is sort of sketched here. So you can go through it, but this is what is done. Right, do you have questions up to now? I know this is a little heavy. Okay. Right, so now having done, if you want pure bosonic and pure fermionic theories, I want to go to do gauge theories. So that's the next level of complication. Okay, so we owe this to Ken Wilson, who first thought of this formulation. But for me, the real birth of lattice QCD happened in 1980 when Mike Croyd simulated SU2 on a lattice. So that was the first simulation of an SU2 gauge theory. So what are the basic steps? Well, the recipe is simple. We discretize space and time. We rotated already. We are in Euclidean space. We usually take isotropic lattices, so lattice spacing the same in spatial and time directions. There are people that do anisotropic lattices, so we will see that tomorrow. So we have a size of a lattice which is ns to the cube times the time direction. Usually the time direction for zero temperature calculations are longer than the spatial direction. Remember, we're in Euclidean time, everything is equivalent. There is no, the only distinction is the long time direction signifies the temperature of the system, and if it's longer, then we are doing zero temperature QCD. If it's shorter, then we do finite temperature QCD because that is determined from the length of the time direction. We know how to define fermion degrees of freedom on a discrete lattice. Now, the gauge degrees of freedom, they're a little bit more complicated than the scalar field that we have seen. And this is why I want to talk about them. So we need to take the continuum action and discretize it appropriately. We have to define the measure like we did before. And then we have to construct the operators that we want to do in order to extract what we want to measure and compare with experiment. So these are the steps that have to be done. Okay, so now I want to talk a little bit about how we discretize gauge degrees of freedom. Now, when we discretize a theory, we break symmetries. This is unfortunate, but there is no way to discretize a theory without breaking symmetries. For example, I no longer have continuous translational invariance on the lattice. I have only discrete translational invariance if I hop from one side to the other. So I break continuous symmetry. I break rotational symmetry because I can only rotate at certain angles. So symmetries are broken and they're only recovered in the continuum limit. Now, one thing that Wilson insisted on, and it's very important, is not to break gauge invariance. Okay, so that determines how we define the gauge fields of the lattice. Now, we know from continuum theory that this quantity, if I want to go from X to another point in space, I do this by having this path order exponential where the gauge field appears here. I guess this you have seen, right? This you have seen. Okay, motivated by this, I will define this exponential here. When I go from X to X plus A, one lattice space. So this is this quantity here. So assume it's very small. So I approximate the integral from X to X plus A by A times that thing, okay? I assume that it doesn't change very much within one lattice space. And I define this thing here, this exponential here, to be U of X in the direction mu, okay? So this kind of thing is defined outside X. If I discretize the X now, it's a lattice point, but it has a direction in the mu direction. So this defines a link that takes me from X to X plus A, because if I do this integral here, here is X, this will be X plus A. So that's how these links are defined on a lattice. They're defined on links to preserve gauge invariance. Okay, and you can convince yourself that if I go backwards, this is of course e to the minus A, and there is a relation between the dagger and the backward going U. Okay, so here it is now. We have the fermions that transform under a gauge transformation with this U matrix, V matrix. And we have the gauge links that transform in this way. And therefore, if I go from X bar to X and join by these links, I can show that if I apply the gauge transformation, this will be invariant, this will be gauge invariant. Okay, so this path is gauge invariant. Like, you know, in continuum theory, right? Because of this path order exponential that you have to put if you want to go from one X to another X in space, in space-time here. The other thing that is gauge invariant is if I have product of links that close themselves. You can convince yourself that if I have U that goes around, so this way, and then it has to go the other way and the other way, and that's why it has a dagger, because it goes in the opposite direction. It goes to mu, and then it goes to minus mu, and we said that this is related by a dagger, remember before? Therefore, that's why these daggers appear, because I go the one way and then I go the opposite way. So if I go and close this, and I apply this gauge transformation, then this is invariant. So this means that I have to construct everything in terms of these gauge invariant quantities. And this is exactly what Wilson did. So the simplest, oops, excuse me, I went too far. I went really too far. Okay, the simplest Wilson loop that I can construct is the one that goes around a square of length A. That's the smallest I can construct. This I will call W1 by 1, okay, 1 by 1. And this I will call plaquette. This is an elementary plaquette. And you see it has two indices, because I go one direction like this and one direction like that, and I have to do it over all the 4-dimensional lattice. So, yes? Yes, exactly, exactly. Okay. So in this way, I preserve gauge invariance even at a given finite A. And this is important to preserve gauge invariance. So the gauge invariance is preserved, although I break other symmetries. Okay, so I have to construct everything now from these gauge invariant quantities. Okay, before we do this, okay, so it boils down to that okay, let's take U1 theory, which is the simplest. Let's take U1's theory. So I have this Lagrangian, And if I now want this to be invariant under gauge transformations for U1, then I need to do the covariant derivative to absorb the phase. So this is by Lagrangian. This is my U that we said before. And now I construct the plaquettes. This is the elementary plaquettes that goes around that we wrote. And then I represent this part of the Lagrangian with the sum over all these plaquettes. And now we want to do the exercise that if I now expand this and take the continuum limit, I recover F mu nu. Now, this is an exercise you can do. I'm not going to go through this. It's written here. But you can go take the sum of this plaquette. Okay, this is it. This is the plaquette. This is my U1 field. So I go round. This is what it is. And I take the limit a goes to 0. So I keep only leading terms. And then this in the continuum limit, classically, will give me F mu nu. Okay, so this the exercise you can do. So if I take these plaquettes, indeed, I will recover this part of the Lagrangian. You will have the slides. I mean, I will write. I can. So very well. So now we can be sure that if we take the sum of the plaquettes, apart from a constant, this is convention, I will recover the F mu nu that I want of the continuum theorem. Okay, this you can do yourself. I mean, as I said, you can expand and show this, that you really get the action of the continuum theory. Okay, by expanding. So everything is fine. So I know now how to write the gauge part of the action in the discrete form. And now we are ready to go. Okay. Now I generalize this for SUN or for SU3, which we're interested in, by writing the link in terms of the Gell-Mann matrices. So here they are. Now it's not just the phase. These are 3 by 3. But it's the same exercise that I have to do. I define the plaquette in the same way. And again, this is a little bit more complicated because now I don't have commuting things. I have to be careful with anti-commuting matrices. So I have to be careful when I expand. But again, you can sit and do the expansion, keeping the commutators and everything. And then you will come up with the correct F mu nu. So this is the correct action also for SU3, where now beta here is 2n divided by the coupling constant square for SUN. So this is the gluonic part of my action in the discretized form. Okay, so this is what it is. And again, as I said, you can go and expand, and I have written it for you here, and you recover the correct continuum limit. You can go through it yourself with the help of the slides. Okay, now, and we will see this in a minute, of course, in the continuum limit, this will give me F mu nu. But I can add higher order operators that will go to 0 as they go to 0. Now, why I mention this here? This is important because as we will see, we will want to do improvements to this discretization, the simplest discretization scheme that I can do. This is maybe not so important for gluons. It is very important for fermions. So I can always add higher dimensional operators, and we will see a simple example in the next lecture, that are irrelevant because it goes to 0 in the continuum limit, in order to improve my discretization scheme. Because when I discretize, this is only true if I take A go to 0. Otherwise, I have corrections to the action that depend on the lattice spacing. And if I can get rid of one term, the next term, then this is better because my discretization is more accurate, and I can do my simulations at larger lattice spacings. So I can do them faster, and this is important. So this is a whole, I mean, it sounds simple, but you have to really work it out. It's, you know, the operators, etc. This is called improvement, and we will see that this is very important when I do fermions. Okay, so here is a summary of what we have done. What I have written here, you may have not realized, but I have written here is that this type of discretization gives me the continuum limit with corrections that go like A squared. You can convince yourself that there is no A. The first correction that appears, if I do this discretization, is A squared. So this is what we call order A improved already, automatically. So the first correction go like A squared. Okay. Okay, I mean, this I have only shown the classical limit. We have to verify that when I do the quantum effects, does not spoil this. And in fact, okay, my A squared might be multiplied by some function of the coupling constant when I have quantum effects. But okay, I mean, I just write this as a comment just to be careful. And I think I will not say any more because it's already 1 hour, but I mean, this is just a word of caution. Okay, so what I wanted to do in the next few minutes is to give you some examples of what quantities we can compute. What do we do? We have a break now or continue? And then we continue. Okay, so you see I have a few more slides, but we have the main ingredients now. Now, these are examples. If you let me go through very fast, just to give you an idea, and then you can go through it yourself. These are now examples of some quantities I calculate on the symbol ones. One of them is the Wilson loop. A Wilson loop is defined as a closed loop like this, where I put a quark and anti-quark distance r. They're infinitely heavy, so they only propagate in time. Okay, and this is equivalent as joining everything with gauge links. And this is called a plaquette. This is called a Wilson line, a Wilson loop. Okay, so I have these creation operators here. I create a quark and anti-quark. I propagate them, and I'll annihilate them at a later time. So they are infinitely heavy, so they only have time evolution, no space evolution. Okay, and I want to compute this quantity. So I want to compute the expectation value of this quantity. So here is a path integral. I have integrated all fermions out, right? There it's sitting in here, and this is my W, right? This is my W here. And I have to do this integral, and of course I will have to simulate it. So we will say how to simulate it. Simone will give you exercises, how to do this. And now if I compute this expectation value, we will see in a minute that this is proportional to the time evolution, goes from Ti to T, times the potential between two static quarks. So this is how I compute the, remember I showed you this lattice data of confinement? This is how it's been computed. By computing the Wilson loop, I get the logarithm of that will give me the potential as a function of R, this distance here, okay, in between them. And this will give me the linearizing potential. So that's how this is computed that I showed you in the beginning of the lecture, just so that you get a feeling of what we can compute. And this explains to you why this is really the potential by starting from a simple quantum mechanical system in non-relativistic physics. If I compute the Green's function, namely the evolution from R to R prime, and I take the mass going to infinity, I will really get the potential. So this is similar. I mean, it's just a motivation. And if I go to Euclidean space, this is exactly what I get by computing this Wilson loop with infinite mass quarks. Now you can go and do this exercise and see that if I have a loop which is J by K, so this is a rectangular, right? J by K. And if I assume linear potential, then I will get K times J here with some constant, with A squared, because it's an area, right? It has dimensions of an area. So A squared to be dimensionless. So this is nothing else but an area law, which is a signature of confinement. Okay, that's why we say this is a confining potential. You can go and do this exercise. And if you take the log of this ratio, you will discover that this is A times sigma, where sigma is called the string tension of the potential. Okay, so. Okay. This is another example what this Wilson line means, which you can go through it. You can actually calculate explicitly what is a propagator because it becomes very simple. You can do it, I have given you the algebra, and you can show that this Green's function is practically a product of gauge links. So you can calculate the propagator of a massively heavy quark in this theory. Okay, this is an interpretation of the string tension. Again, you can read it. It's a simple model that motivates how this string tension that we saw from the Wilson loop may be related to something physical. Again, it's written here. I don't have time to go through all the details, but it's a simple model that shows you that this, you can get an estimate. It's only an estimate of the string tension from this simple model. And this is actually a breakthrough calculation for its time. You see, it's 30 years ago, where for the first time we could actually determine the flux between a Q and a Q bar. A very nice picture. You see how it is. The flux tube between a Q and Q bar. This is a simulation. And this is a very well-known paper that shows that. Okay, I don't think I have time to explain a lot about the continuum limit. Either you read it or we revisit it if we have time in the next lecture, because I think this is a little separate now from what we have discussed up to now, but there is a well-defined way to take the continuum limit in lattice QCD. Maybe I stop here, and then if we have time, we can revisit it, or you read it and we can discuss. Okay, thank you. Okay. I guess, should I start? Okay, I know this is a bit maybe too much today, but tomorrow we will see more practical things, I hope. But I thought I will give you the basis. Okay, let's see. So this is the second part of the lecture. And what I would like to do mostly here, we saw the gauge part. We construct this Wilson loop, for example, which is all product of these U fields. Now I want to tell you a little bit about fermions and why they're difficult. Although I can integrate them out, they're still difficult. And the motivation really here is for you to understand why we have different formulations of lattice actions. I mean, maybe you have heard Clover fermions, twisted mass fermions, staggered fermions, right? So domain wall fermions, why so many variations? And my hope here is for you to understand at least the basis of this. Okay, so that's the motivation here. And this is why we want to see what is the problem with fermions and how we solve this problem, which gives rise to these different kinds of formulations. Right, so the fermion action, as we said, the fermion action, here is my, this is my continuum part of the action. I didn't write the mass, so I put the mass to 0, is psi bar d slash psi. This is the continuum term in the Lagrangian, and I make the derivative into differences. And I make the derivative into differences in a gauge invariant way. So this is why these U's and U daggers appear here. I don't know what this says, C's. I don't think this is a typo. Okay, so this is a discretized form. So this should be a square bracket, I think. This is a discretized form of this continuum derivative. And again, you can convince yourself by expanding this link that indeed, if I expand it in the continuum limit, I get what I should get. Okay? So again, this has corrections of A squared. And here I also put the mass. And the mass is diagonal here. So this will give me something which is off diagonal plus the mass which is diagonal. So this will define me this matrix M, which is explicitly given here. So this is a matrix that is sparse. It has elements on the diagonal and in the off diagonal. So it's a sparse matrix with boundary conditions at the corners. Okay, that's what it is. This is very important. The thing that is a sparse matrix makes the computation feasible. If it was a full matrix, this would be much, much harder. Okay? Okay, so this is the bilinear form that we have seen in the first lecture. So we are good. We can integrate the fermions out because we have exactly the form that we saw in the previous lecture. Okay, I use Euclidean gamma matrices, which are given here. It doesn't matter. I mean, this is what they are. I mean, they're the usual one, apart from an I in front. And now, if I go and compute the propagator in momentum space, I will get not m plus p slash, which is a continuum propagator, but I will get gamma sine p mu. So I will get this sign combination, which in the continuum limit, if I expand the sign, I will recover the continuum propagator, m slash p. Okay? And now, if I rotate in Euclidean space, which means P0, which I would call P4 here in the fourth direction, is my time direction, becomes IE. This sign here will become a sinh, and therefore, this is the condition of my pole. Okay, this is the relation between the mass and the energy in my Euclidean lattice. Okay, so if I expand now this, I will get the continuum limit, the continuum expression up to corrections of A squared. So that's why we say even the free discretized fermionic action has corrections of order A squared. So I will see deviations. If I do a simulation, I will see that this is satisfied, the dispersion relation will be satisfied, but it will deviate for large P or for coarser lattices, for large lattice spaces. Okay, so what are the symmetries of this naive? What we will see is a naive fermion action. Well, this is invariant under a phase, right? Gauge phase. And it's also invariant in the massless case under a chiral transformation. Okay. So this is all good. Okay, I have some comments here, but let's not worry about this at the moment. Okay, so now we have seen how to generalize from the fermions, from the gauge, from the post-zonic degrees of freedom, we are the gauge fields, to the fermions. The basic difference is the minus signs that arise from the antisymmetry. But we have an additional problem with fermions. You know, fermionic states are antisymmetric. And if I do a Euclidean time evolution, this always goes to the lowest state, which is usually a symmetric state. So unless we make an explicit projection to an antisymmetric state, we will always get the wrong state. Okay, so this exact projection is done by writing the integral as Krasmanian variable. This is what we basically have done, and integrate them out. And as we have already seen, the price is that my action from local, it became non-local. And this, for many years, causes problems. And this is why maybe you have heard 20 years ago, we have done simulation by ignoring the determinant, by saying the determinant is a correction, because if you write out what the determinant is, these are Koch loops. So we sort of froze the sea, and we did the simulation in this, what is called quench. We quenched the dynamic degrees, the clock degrees of freedom in the vacuum. So that's an approximation that we did in order to be able to do the simulations, because this was very difficult to simulate until some time ago. Now, this is really very important. I didn't put it in red, but maybe I should, because this is the origin of all the different types of fermions. And we will see this in the next slide. This naive fermion action suffers from what is called fermion doubling problem. And we have to correct for it. Okay, and this is the answer to you, Alessandro. If you have non-relativistic systems with two-body potentials, which have 4 fermion, then you do this Hopper-Sladanovic transformation to integrate out the quadratic potential term on the expense of introducing additional degrees of freedom. Okay, but this can be done, but still this doesn't get rid of the sign problem. So you have the sign problem there, and the simulations cannot be done really. Okay, so let's see what is this fermion doubling issue is. So let me take now this discrete version that we wrote down in the previous slide. This is the discrete version that we wrote. This is the mass term, right? And as we said, if I expand, I really recover the continuum limit. So this is not an issue. I recover the continuum limit. However, now let me examine the eigenmodes of this naive Hamiltonian, and I will set them as equal 0 for simplicity. Okay, so I have, this is my derivative times p bar gamma 1, right? This is the symmetric derivative. I take n minus 1 and plus 1 divided by 2a. In the limit, this is the derivative. And I took the free theory, so I said u equals 1 again for simplicity. So this problem arises even in the free theory. Okay, but this now I can solve. I can find the eigenfunctions of this naive Hamiltonian. This is what it is, right? And if I go there and put it in, I recover what I expect, namely the sign of Ka that we had before, energy equal the sign. That's what we had before, right? And if I expand, I get the correct thing up to h squared. Okay, now, however, so this energy has the correct dispersion relation for k goes to 0. So at k equals 0, I recover the correct dispersion relation, this one here. Okay. However, this sign has also a 0 at pi k at the end of the Brillouin zone. So it doesn't only have a linear thing at the origin, it also has a linear thing here, right? It has a node both here and here. And therefore, if you compute the group velocity, you will find that we have a 0 here, we have a 0 here, and we have a 0 here in the end of the Brillouin zone. So what this means is I have 2 poles, which means 2 degrees of freedom. One has the slope like this, the other has a slope like that. So right hand moving becomes left hand moving. So this is the origin of the problem. Instead of having 1, 0, 1 pole, I have 2. And this is in 1 dimension. So if I have 4 dimensions now, I have 2 to the 4, 16. So instead of having 1 electron now, I have 16 of them, 16 copies. And that's the problem. This is called fermion doubling problem. Okay, so it's very simple, yes. It's only fermions. And the reason in the dispersion relation is different. It's a second derivative, and this is what will cure it. Okay? This is a first derivative. That's the problem in the Dirac equation. That's exactly, very good, very good. Okay, so this is our problem now. We have the right continuum limit, but we have 16 species instead of 1. Okay, this is connected to this no-go theorem that I mentioned in the previous slide, which I'm not going to prove anything. But for a long time, we thought this is incurable. If we had to do something, we had to break something. And at the beginning, this is how we did it. Okay, so again, the solution came. Let me see what I do next here in this slide. Yeah, I mean, this is an explanation of the whole thing. So here I give you where the zeros occur and why they're 16, right? I do it in 4 dimensions and show you that indeed this, like we did it for 1 dimension, in generalizes to 4 dimensions. Okay, so this is the explanation here. Okay. So Wilson came up with a prescription how to cure this. And what he did actually is to include a second derivative. This is a second derivative. It's a discretized second derivative, right? Cn plus 1 minus 2 Cn plus that. This is a second derivative. Times A, so this is an irrelevant operator, it goes to 0, it's equal to 0, but it modifies the discrete action. So now if I go and do the same thing, this is the free theory again, I put U equals 1, M equals 0. So if I go and compute the energy spectrum now, like we did before, what we will find is sine squared plus this term. And if I expand now, I find the correct thing, the dispersion relation plus corrections. Now, when K goes to the Brillouin zone, what I get is 2A over A. As I let A goes to 0, this goes to infinity. So that they become infinitely heavy fermions that decouple from my theory. So they're irrelevant in the continuum limit. So that's how Wilson killed the doublers. So he killed the 15 doublers on the Brillouin zone and left the one that we're interested in. Aha, very good, very good. However, there is another problem that arises now. We said that in the massless limit, this is chiral invariance is preserved. No longer. Because this guy here, for finite A, it's acting like a mass term. And therefore, it breaks chiral invariance. So you can see it explicitly here. Here, I rewrote the action, which I now call Wilson action, because I added this second derivative. And you see this term here, you remember here, this term here. This is the mass. This will introduce a mass term. It's psi bar psi. It's no longer off diagonal, it's on the diagonal. Okay? So even in the massless case, you will have something on the diagonal. And this is this term here. 4, if I write it like this, it's 4R over A. And even with 0 quark mass, this remains. So this breaks chiral invariance. And this is exactly not what the no-go theorem said, that if you want to have a local theory, local quantum field theory, and discretize it, you cannot avoid couplers unless you break chiral invariance. You cannot have locality, chiral invariance, and no doublets altogether. This was the no-go theorem. Okay, and that's what it is. So we broke chiral invariance. Okay, we broke chiral invariance. We recover it in the continuum limit, but on the lattice, all the what identities we know in the continuum and lab are broken. Renormalization gets more difficult. There is additive renormalization that has to happen. So things get more complicated now. Because you break symmetries, your life gets harder. Okay, so bear this in mind. Huh? So we solve the doubling problem, and this is what we call Wilson fermion. So when you hear the term Wilson fermion, this is what it is. This is because we have to discretize the action in this particular way. Okay, so what we usually do, just to give you the framework of the simulations, we rescale the U's according, so we define this K to be a combination now of the mass and this parameter R, which we set usually to 1. It's arbitrary, we set it to 1 usually. And now this is the coupling constant, which is defined in this combination. And you see at 0, this is 1 over, when the mass of the quarks goes to 0, this is 1 over 8. This is called critical copy parameter. We redefine the fields in this way, so that is convenient. And we write the quark mass in terms of 1 over kappa minus 1 over critical, when n equals 0. And this gives our quarks the mass. Okay, so by tuning K, we adjust the quark mass to reproduce whatever physical observable we tune it to. And we will see this, how this is done. Okay, so this is how we define now the fermionic action. Again, this is a matrix. It's M, psi bar psi. We can integrate out. It's a different M, right, with this R parameter. But they said everything goes through because it's bilinear again. Okay. So this is now the Wilson, what we call the Wilson propagator of the Wilson action. We can write it in the free case. We know what it is. And now this matrix M that appears, so this propagator, which is the inverse of this M, has certain very nice properties. It has this gamma, what we call gamma hermiticity. It's Hermitian if I multiply left and right by gamma 5. So that's why it's called gamma hermiticity. This is very good because in simulations, it's easy to do. So this action still fulfills this gamma 5 hermiticity. Right. What else do I want to say here? Again, you can derive what the poles are. In Euclidean space, you will find that the poles of this guy here is given by this relation. Right. Now, if you expand this now, because now we have this cosh here and this change here, these will have corrections of order L, not of order A squared. This is a problem because everything else up to now was order A squared. We didn't have order A. Now this has what we call well scaling behavior because it has corrections that start with A. And this is what I said before. We need to do something to remove this order A. And this goes by the name of improvement, improved actions, because we want these to be of the same order at least as the gauge discretization scheme, which is of order A squared. Otherwise, we have big corrections for finite A. Okay, so now you appreciate we solved the problem. We introduce chiral symmetry break, explicit chiral symmetry break in the finite A, and our corrections go like order A. Okay, so this we have already said. This is a summary of the properties. The heavy tupless decouple in the continuum limit. Chiral symmetry is broken explicitly. Okay, I mean, this is a property you can show if you make transformation of this type and you differentiate with respect to the angle here, the difference in the actions of, between with an operator is related like this. This you can prove. You can show that this becomes this quantity here, which shows you that apart from this pseudo-scalar contribution coming from the mass, you get an extra additive contribution. So the quark mass gets both an additive and a multiplicative renormalization now in this formulation. So the renormalization becomes more complex. Now, in practice, how we compute this critical hopping parameter, where the way we do it is to compute the pion mass. We will see in the next tomorrow how to compute this. From chiral perturbation theory, we know that the mass square is proportional to the quark mass. And therefore, when this becomes 0, then we have the chiral limit, which defines kappa critical, where the mass goes to 0. Another way to compute this is to use the word identity here, the actual word identity. Again, we can compute the mass and then find the kappa critical. So as we said, we can do it either way, and the two ways will agree up to oppose the discretization errors of order A. So only if we take the continuum limit, we are guaranteed that this will agree. This is important to realize. In any lattice calculation that doesn't take the continuum limit, there are corrections. Okay, I think I'm not going to say very much about this, but I mean, for those who know about the anomaly, one can show that the anomaly is recovered on the lattice. But okay, I'm not going to go into this. It's just for people that may wonder what happens to the anomaly. Okay. So, in the discretized form, the spin and flavor degrees of freedom have a one-to-one correspondence with the continuum Dirac fermions. We have the 4 degrees of freedom that is the same here. We have a 4-component spin or in each lattice side. These are the complete equivalent of the continuum theory. We have the U, then D, etc. The flavors are equivalent. There is nothing strange about that. And the action is still invariant under a gauge transformation. So we have a conserved current. The electromagnetic current is still conserved on the lattice, exactly. And this is an exercise. You may want to go and do it to show that this is the conserved current in the discrete form. So if I use this electromagnetic current and compute anything on the lattice, then I don't need a renormalization constant because it's a conserved current. Okay, this is not true for the axial one. So this continuum, this discrete form of the continuum electromagnetic current is conserved exactly on the lattice because the symmetry is preserved. Whereas this one is not, and therefore we really have to renormalize it because it's not conserved. Okay, so now let's consider another way of solving the doubling problem. This is the Wilson-Fermion type of correction. Okay, this is called staggered fermions. And here I'm showing you it in 2 dimensions because this is what I can draw. So in 2 dimensions, we will have 4 couplers. And if we split the spin, so if I use the freedom to define the spin on the neighboring side, I have basically diluted the spin. In some sense, I made it non-local. The spin is, I mean, my fermion spinor is no longer defined on one lattice side, right? Like before. In the Wilson case, each lattice point has 4 components. Now, if I distribute this, then I make the theory non-local. And the no-go theorem says, then you can kill some of the doublers because you made the theory non-local. And you can do this, you can take the hypercubit and divide by 4. That's the maximum you can do, right? And then from the 16, you would be left with 4. You still have 4 doublets, but you reduce it from 16 to 4. Okay? Okay, this is how you write it. It's complicated. I don't think I'm going to go into details, but this is how you define this type of fermions, which they are called staggered, because they are staggered in different, their legs are not in one place, but in 4, let's say. Okay, so this has other problems. It breaks flavor symmetry because it mixes the flavors, but it preserves chiral symmetry. So this is what is used usually when you do finite temperature calculations, where you want to preserve chiral symmetry, where it's important. This is not usually used for structure because it's very complicated to compute and disentangle the mixing of the flavors. So that's why I'm not going to say very much because we will not use it further on. But now you understand why we have these different types of fermions. Okay, now this is you still have a 4, yeah, you have 4 tastes. And you have to disentangle them. And this is why it's horrible. I never used it, to be frank. It's just that people use it if it's important to preserve chiral symmetry. Now, this is a schematic explanation why you get rid in 2 dimensions of half the doublets. So in 2 dimensions, I have one spinor here, and then in the next one, in the next lattice size, I have the other half. And then, okay, so basically what I do, it repeats itself every 2A and not every A. So instead of having these modes, I go to these modes where one is missing, okay? So this means that the maximum momentum is pi over 2A because it's as if I have doubled the lattice spacing now. And that's why this gets rid of one mode. Okay? It doesn't go to pi over A, it goes to pi over 2A, and I'm fine there because it's not 0. I don't have a mode there. Okay? And that's why it cuts the degrees of freedom in this two-dimensional model by a factor of 2. Because effectively, it's like I have seen the modes by a factor of 2 because the lattice spacing is effectively twice the lattice spacing. So roughly, so just to give you an intuition why this works, without going into complicated mathematics. Okay, I mean, you can do the exercise with the free theory and show that the modes are like this. Okay. I would skip this. I mean, we said it all. I mean, it has nice properties and people can do very fast simulations. I mean, this is an action that it's order A square improved. So you don't have to do anything. You can go and put it on the lattice and do simulation. But then it has these other difficulties that you still have mixing of the flavors. Okay, and now I want to tell you, we said that the Wilson fermions, which is the ones that are mostly used for spectroscopy and structure, it's order A, improved only. And this is a problem. And now with this little example, and I think I have 5 minutes or so. How many minutes do I have? 5 minutes, okay. With this simple example, I want to explain to you the basic concept of improvement. Suppose I want to discretize my first derivative. Here is my continuum first derivative, and I discretize it like this, symmetrically, like I did for the Dirac operator. Okay, if I expand, if I do a Fourier expansion, I will only get odd terms here in terms of lattice spacing, because 8 to the second will cancel. Okay, so this is a very nice discretization because I have only arrows starting at A cubed. Suppose, however, I want to get rid of this term. Okay, then, okay, this is my Taylor expansion. I will add something which has an A cubed, like this term, because I want to cancel it. And this is the discretized version of the third derivative. So if I go and do the algebra, and I put this coefficient here, -1/6, you can show that this term is eliminated. So I improved my discretization scheme. Of course, I made it more complex because this is much more difficult than this. But I now got rid of this. And in fact, okay, I mean, this is automatically, I mean, it will start with A to the 5th now. So this is the way I can get rid of higher A terms with the expense of making my action much more complex. Okay, so it has to be worth it. So the A term is eliminated and my action is improved. Okay, this is sort of what we do in lattice QCD. So this is the original Lagrangian. And then I have higher order operators that are multiplied by powers of A. I have to preserve the dimensions, so these are higher order operators because it's multiplied by powers of A. Okay, and then I have to find these higher order operators, all of them, add them, determine the coefficients, which is non-trivial. So it's a highly non-trivial program that I have to do, in order that I eliminate the next order term. Okay, this is what we do. This is what we do to improve to order A, to eliminate, in other words, eliminate order A terms from the Fermion action. Okay, so this is what we do. So in the case of Wilson, I will add this higher order operator here. You see, it's A to the 5th here. And And this, I symmetrize it, and it looks like a clover leaf. So that's why it's called clover. And this has the property that it eliminates the order A term. You can expand, and you can show that it indeed eliminates that. But you see, I have to calculate this coefficient here. Either I do it in perturbation theory, or I do it non-perturbatively. But I have to determine this coefficient, which is called the Clover coefficient. And then I have an improved action, which is called Clover fermions. So you have heard probably this. These are Wilson fermions that eliminate the order A term, and therefore this is order A square. So the next, it's order A, we say it's order A improved. Okay. Now there is a complication that if I improve my action, I have to also improve the operator. Because I will have this in the action plus higher order terms. If I start expanding the action, I have to also do the same with the operator, because when I discretize my operator, it's also discretized to a certain order in A. So it is not only necessary to improve the action, I have to also improve the operator to have a consistent improvement program. And this is what is done in the real simulation. So in Clover fermions, I improve the action by putting this Clover term. And at the same time, I have to improve my operators. So it's complicated, but we know how to do it. Just to give you a flavor now, when you hear Clover fermions, you think what it is. Yeah, but here we have A terms. Here we have so we have a to the 4 term here. I mean, if I write this as an integral, it's a to the 4. This is the first order after this. It's right. Okay. Now comes what me and Simone are usually doing, which is called twisted mass fermions. I'm not going to say a lot, but just because you're going to hear tomorrow results about twisted mass fermions, you will say, well, what are these? We said Clover, now what are twisted mass fermions? Okay, now if I take the continuum action and I add a funny term, which is I mu gamma phi tau. This is the Pauli spinor. If I write this, then I can write this mass-looking term like m with some exponential. And if I make a transformation which looks like a chiral transformation, but it's not really because it has this tau here. If I make this transformation here, I recover the standard Dirac action. So whether I write it like this or like this is equivalent in the continuum limit. I mean, in the continuum. If I'm in the continuum, it makes no difference, because I rotate and I get back to here. I make this transformation and I'm back here. So I do nothing. However, if I discretize in the discretized form, then I get a different discretization action. And why is this important? I'm not going to show this because this is a very complicated proof. You can find it. This is Giancarlo and Roberto Rezzotti. They have proved that if you do this in the discretized form, then you do not need to improve the operators. If you just improve the action like this, you do not need to improve the operators because all terms that are proportional to A vanish automatically. Okay, this is why it's called automatic order A improvement, because you do not have to improve the operators. And this is a great advantage because we don't worry about improving the operators. We take the naive operators, we calculate the expectation values with that action, and we're perfectly okay. We preserve order A improvement. We do not have order A terms at all. The renormalization is easier because I don't change my operators, and therefore life is much easier. Okay? This one has to prove, but it is proven, okay? Of course, as the Americans say, there is no free lunch. We got something from free. No, I don't want to mess with my operator. However, okay, we break chiral symmetry. This is true with Grover fermions. This is true with any Wilson fermions. We break chiral symmetry explicitly. This is all true with all Wilson fermions. However, now we also break flavor symmetry because of this term here. And pi 0 is no longer degenerate to pi plus pi minus because we break flavor symmetry. And this causes some complications. But if I only use charged pions, then I am fine. But it has this disadvantage that flavor symmetry is only recovered in the continuum limit. Okay, so you see, my message here is every discretization scheme breaks something. And you choose the one that is best fitted for what you want to compute. Okay, so that's the message. In the continuum limit, all should give the same results, but only in the continuum limit. Okay, so when you read lattice papers, be careful. And this is difficult because every time you do a calculation, you have to do it at several lattice spaces. This is very expensive, and you have to take the continuum limit. We didn't go a lot into taking the continuum limit, but basically what you do, you calculate at one lattice spacing, you calculate the next lattice. Usually you need at least 3 or 4. These are very expensive calculations, and then you have to take the continuum limit. Only in the continuum limit, you are guaranteed that you will agree, both with experiment and between each other. Okay, so that's the message. Be careful when you read lattice papers. Right, so these are the type of fermions that I wanted to cover. There is another type, which is the most sophisticated one, that it's called chiral actions. They preserve chiral symmetry. They are order improved, but they're much more difficult to simulate. One is done, it needs to do it in a 5-dimensional lattice, so you add another dimension, so it's much more expensive. And the other one, it's called overlap, where the operators have square roots, which is much more difficult to compute. So just to know that there are these actions, people use them. They are very nice actions, and they rely on the fact that you overcome the no-code theorem by using a generalized relation, which is given here. I'm not going to say a lot, but the message here is you have these actions which preserve chiral symmetry, very nice properties. They are more difficult to simulate. I mean, overlap, I don't know anybody who is simulating them. Domain wall, there are people in the US that are simulating this. You need an additional dimension with all the complications that come with it. because it has to be large enough not to mix the walls, etc. But these are very nice actions, you know, and eventually we may, if we have big resources to compute this. So these are the actions that we have. Okay, and we will see tomorrow how we do calculations now using these particular actions that I talked about, okay, and how difficult they are and what is the computational resources that we require for that. Lattice QCD relies a lot on improving algorithms. It's not just getting bigger machines, it's also improving algorithms. And I will close with that. I mean, this is better algorithms, how they scale as I approach the physical pion mass. This is the ratio of the pion mass to the raw mass, the vector mass, the raw mass. This is the physical point. And you see how a worse algorithm scales as I approach this point, the physical point. That's where I want to be, as compared to another algorithm. So algorithms are very important because I can approach faster the point that I want to be. And now you appreciate why being here has taken a very long time, because you see the scaling. Okay, how the algorithms scale as I make the pion mass closer to the continuum limit. I mean, this ratio, really, dimensional ratio, how I make it approach the continuum limit. Okay, and now you see here different, so Wilson, Stager, how they scale, okay? And these are the resources that you would need to simulate. So you have to appreciate this. Algorithmic development is one of the key issues or necessity, let's say, in lattice QCD to be able to get results where we want them to be. Okay, I'll stop here. I know it's a lot, but we are now ready to discuss physics using this formalism. So I hope this is a motivation of doing these 2 lectures. Thank you.